kind of a diagram of what we just looked at, and you have to interpret and work through it and answer multiple questions on it. So let's just kind of get, our bearings here with this question. So we have the energies of an electron within an atom are most often given relative to ionization as shown below. Determine the energy of a photon absorbed or released as an electron makes a transition from D, okay, so from D, so that's where I start, so I'm going to say that is my E initial, to B, which is E final, okay? So the energy of the photon absorbed or released is just delta E is equal to my EF minus EI, which is -10 minus -2. So include the negatives and positives when you do your actual calculation. So I'm going to get -8.0 eV. Now, if I was just giving my answer straight, I could say, well, it was just 8 electron volts. Okay, so it's 8.0 eV, and since it was negative means, think about the photon, if it's negative, then it's being released, okay? Next one. Determine the number of photons of different wavelengths that could be possibly produced due to an electron at level C moving to ground state. So say you have C, B, and A. A is our ground state. So either you could have it move from C all the way down. So whatever photon is emitted at doing that, that's like one scenario. Okay? Or say it started at C and it just moved down to B, emitted a photon, and then moved from B to A. That's another photon. So there are 3 different possible wavelengths of photons being emitted. Because think about it, this is the change in energy of a photon, the change in energy of a photon. Now, if we think about it, we can have our E is equal to hc over lambda. Well, the energy of each photon is going to influence its wavelength. So there's 3 different possible wavelengths that can be released. Okay? Because there's 3 different scenarios to get from C to A. Or three different steps involving scenarios to get from C to A. Next, determine the frequency of the photon absorbed or released when the electron in the atom moves from C to A. All right, so if we look back at C to A, so from C to A is my E final, and C is my E initial, because I'm going from C to A. So my A was my -14, and C is -7. So I go delta E is equal to EF minus EI. So my delta E then is -7 eV. But it said, what is the frequency of that photon? So now I can use my formula of E is equal to H times F. Now keep in mind that your E is in EV, so use your H that also has EV. Okay? If you don't, you need to convert your energy. So if I'm looking for F, I go E divided by H. And when you're doing these calculations, your energy doesn't need to be negative anymore. the negative energy just indicated if it's released or emitted, released or absorbed. So you don't need to continue with the so our frequency should get 1.75 times 10 to the 15 hertz. And then it also asked us, is the photon absorbed or released? Well, if it's negative, then it's been...
I didn't get that answer.
Oh.
Did you say it was 1.75 or 1.7?
1.7?
You said 1.75. So is it 1.7?
Okay, so I got 1.69 times 10 to the 15, but we'll use 2 sig digs because in the graph there's just 2 sig digs. Yeah. So then I rounded to 1.7. Yeah.
You said it as
Oh, sorry, I probably did. That's my fault. Okay, so kind of getting the gist of these so far. I know it's a longer lesson, but it's like a thing that we've never really talked about. So, okay, so next, determine the wavelength of a photon required to ionize an electron that was initially at ground state. So that means that you're going all the way from ground state to the ionization one. So what we need to find first is our delta E. So we're going all the way from ground state. So I would put like E ion is the final minus E ground. Okay. So my delta E is equal to 0 minus negative 14. So then I can see, okay, this is positive 14.0 eV, which shows if it's positive, then the photon's been absorbed, which kind of makes sense because you're going all the way from a ground state up to ionizing, okay? So therefore, photon absorbed. And then it's asking you, what is the wavelength of it? Well, we can use our E is equal to hc over lambda. And our lambda then is equal to hc over E. Again, use your H that has EV in it since our energy is given in EV. So wavelength, you get 8.871, and so I'm going to round that to 8.9 times 10 to the negative 8 meter. You know, the last one is kind of the most complex, I find, in